Jiecao Chen is going to give it a go.
Yeah. So, so I'm Jiecao Chen. So this is joint work with Chen Zhang, who is also here. So the problem we started is to do sampling from a data stream which has like near duplicates. The motivation is basically we have a lot of like with some image data and video data. We can have like with some after compression or after resize, there might be like slightly different. But also like for queries of the same meaning sent to Google, they have slightly different form. So the model we consider is like a streaming model, and we also we want to design like space and the time efficient algorithm. Also, we consider sliding window case where we only consider the recent W item. We only consider the data point. In this work, we only consider data point in Euclidean space, but it's very, very valuable because for image data and other text data, you can always learn embedding. So you can preserve the distance between like a complex object and in Euclidean space. So think about that. If we have a magic function which can essentially map all those like similar item, similar point to a unique group ID, then we can reduce this problem to like a standard streaming algorithm. So, but
which problem?
Like the problem is like we want to process the noisy data with near duplicate in streaming model. So if we have a magic function which can map all those.
It's holding time to solve. I haven't seen you set the problem.
Yeah, I will introduce the problem formally, but it's roughly like a draw sample from data stream where near duplicates. So yeah. Okay, so yeah, we're unlikely to have this kind of magic function, so we need some slightly new idea. Okay, let's get to the problem formally. So the problem we want to solve, for the non-noise setting, we say it's an L0 sampling. That means we want to sample from the distinct element, where each element is sampled with probably 1 over F0. F0 is essentially the number of distinct elements in the data stream. So is it clear? So for robust L0 sampling, that means in the data stream, we might have like some similar data points. We want to treat all those data points as one group. So we essentially want to sample from those groups. Each group is sampled with probability 1 over F0. Again, here, F0 here is like a number of groups. So it's no longer the number of distinct elements, but now it's a number of groups. Here is the example. Here we have a bunch of data points, and we can group them to like 6 different groups. So we want to like we want sample from those groups. Each group is sampled with 1 over 6 probability. To handle this problem formally, we need to introduce some extra notation where for data set in Euclidean space, we say it's an alpha beta space. If like it's either for any 2 data points, it's either like smaller than alpha or its distance is larger than beta. So when beta of alpha is larger than 2, then we can, for adding data point, we can define the group naturally. It's all the distance smaller than alpha. And for such data set, we say it's well-shaped. And there's a nature partition for this kind of data set. So F0 is defined as a number of groups. So mostly of this talk, we will consider the well-shaped data set. But our result can extend to like a general data set, which is like there's no nature partition. And yeah, we will talk about that later. Again, our goal is like we want to, when we say sample a group, we mean sample point from that group. So we don't want to like sample all the points from those groups. We just want to sample 1 point from that group. And the goal is like after the pass, we want to output a data point, which for each fixed group, the probability that this data point belongs to this group is exactly 1 over F0. For this presentation, we focus on 2 dimension and 2. And this this work can also extend to general dimension, and yeah. So okay, so let's get to the infinite window case. The basic idea is very simple. So here you have a data stream, and in our case we have 3 different groups, right? they are represented by different shapes. And the idea is we mark, for each group, we mark one representative point. Here we can define as a data point that arrive first of this group. So here we have 3 different points. If we can draw samples from those first arrived points, then we're done, right? Because the group can be represented by those points. But the question is, can we identify those first arrived points of each group space efficiently? So let's think about. Let's look at the difficult. Okay, so the issue is essentially you need to maintain all those first arrived points, because if you slow them away, then you have no way to, if later there's a point of the same group comes again, then you don't know whether it is a first point. So we essentially need to keep all those first points. Neither way is true. But what we can do, the solution is we can place a random grid in the space. So we place the random grid in the space before we see the data stream. And another issue is we need to decide and we sample cells instead of sample data points from the grid. I will show you a picture. So another issue is we need to decide the sample rate, because if we sample, if we use very high sample rate, that means a lot of cells will be sampled, so we use a lot of space. Here's an example. So we have 2 different types of cells, blue cells, sample cells, as I mentioned. And for group, we have 3 different types of groups. Accepted group, which means the first arrived point is falls into this cell, into a sample cell. An ignored group, that means no point falls into a sample cell. For rejected point, that means there's a point that its first point falls into a non-sampled cell. Now let's get to the question, so how can we maintain the accepted point? For a data point which falls into a sample cell, we can for sure, we just keep it. But what if a data point is fall into a cell which it's near a sample cell? Shall we discard it? Shall we? So the problem is if we discard this point, then later we have another point of the same group comes. Then we don't know whether it is a first arrived point or not. So we have to keep all those that first arrived point, which is near to a sample cell. Yeah. So this is just a way you can look at whenever you have a data point, you can look at its nearby cells and see if there's a sample cell in its sample cell nearby. If there is one, then we just keep it. So we essentially maintain 2 sets. One is for the first arrived point, and the other. And we can show in constant dimensional space, we can just show it's roughly the same size up to constant with high probability. So we can bound the size. Also, how do we decide the sample rate? When the set of accepted SACC is too large, we just simply resample with 1/2 probability. And then we can, with high probability, it's half of the size. So we can bound the space. Now, let's talk about sliding window case. So extend this idea to sliding window case is not achievable because let's see what's the problem. The problem is if we maintain an accepted set, the first arrived point here might get expired, right? So you maintain a set, but some of the data point get expired. So you get into trouble. And here the group is still valid. There's a simple fix is we maintain a pair instead of just a point. Here we maintain the representative point. But we also maintain the latest point in the same group. So whenever we see a new point in this group, we just keep update. And if even the latest date point is expired, then we just throw away this pair. Another issue is even the pair itself get expired. So we couldn't just decrease this sample rate because if we keep decrease this sample rate, then maybe nothing remains for this group. A fix is for each sample rate, we maintain a sampler. So it has a hierarchical structure. Each level monitor a subset of a sub window of this whole window. So it's the window they monitor is a disjoint, and the union is just entire window. And we also have we still have issues, so it's not non-trivial, as I mentioned. The issue here is because now we have fixed sample rate. That means for a certain level, it's possible it has more than a couple. It had too many pairs being maintained. So we need to do resample. We just skip a little bit this technical detail. If we are interested, you can just come to our post section and we can explain a little bit details. Let's talk about how to generate sample at the point of query. So we have the hierarchical structure. Now how can we generate sample? What we do is we're from the top level, and we go through the bottom level. Each level is resampled with some certain probability here, and we union all those sampled groups, and then we just return the sample uniform at random. Here's our theorem. So for a well-shaped data set in constant dimension, Euclidean space, we just use log m space, log m process time per point, date point. And for sliding window, we have a log w overhead. W is just the size of the window. And for high dimension, we need a slightly stronger assumption, but this can be fixed a little bit. Okay, so let's get to for general data set, when the data set is not well separated, we have no nature partition for this data set. What can we do? So there isn't too much we can do, but we still have some theoretical guarantee. The thing we can do is now think about that. If you draw for any fixed data point in this set, if you draw a ball with radius alpha, then the sampler always a sampler can return a point Q, which the probability it falls into this ball is roughly 1 over F0. That is our guarantee for general data set. So I think it might be used for in general. And I mean, in general, in practice, you don't really care about it's exactly 1 over F0, but up to a constant is maybe enough. Okay, so there's some open question for this line of work because we want to reduce this assumption, and also this gradient. Is it possible to extend this to other metric space? So what the time? So how many minutes are left?
We have 9 minutes.
Okay.
But it's fine.
Okay. So I'm pretty much done. So that's it. Yeah.
Questions?
Any questions?
Any questions? No, I don't have a question to ask this time. So yeah. Thank you very much.
Thank you.
Thank you very much.